fac share content.
Ar trebui să meargă share content. Share screen.
Dacă nu o să am intru de pe laptop, da. Vedeți tableta mea?
Da, e bine.
Da. Deci sunt Marius Zimand. Mulțumesc pentru invitație.
Marius?
Pentru cine... Da.
In English, please.
Okay. I have to switch from the break mode to the business mode, yes. Okay, so I'm Marius Zimand, and this is joint work with Bruno Baus. First of all, I want to thank Elena, Gabi, and Sebi for inviting me. I consider myself these days to work in information theory. I studied in computational complexity, but this work maybe it's combines complexity with information theory. So the title is Universal Almost Optimal Compression and Slepian-Wolf Coding. I'm not sure if I have time to talk about the Slepian-Wolf coding. Anyway, let's start. Okay, so this work it's about looking at what is possible and what is impossible in data compression. And the main result is actually in the positive direction. I show that something which perhaps you may think it's impossible is actually possible. So it's about lossless compression. In lossless compression, we have a string X, and we want to compress it to a code word CX. And there are three main objectives. Number one, we want the code word CX to be as short as possible. And by this, I mean the length should be the minimum description length, which I will explain briefly, shortly. But we also want constructing CX from X, which is compression, to be fast. And we also want fast decompression, which means reconstructing X from the code word CX. And it is well known and actually quite easy to see that objectives 1 and 3 are impossible to achieve simultaneously. And the main result that I want to show you is that objectives 1 and 2, on the other hand, and I think this is surprising, can actually be achieved simultaneously. So it's possible to compress to something which is very, very close to the minimum description length. And number 2, this can be done fast. And similar results holds for distributed compression, which is also known in information theory as Slepian-Wolf coding. Oops. Okay, so let me try to formalize this. So the main result formally says that there is a so-called universal compression, and it is fast, works in probabilistic polynomial time. And formally, I have to define what is a compressor and what is a decompressor. So compressor is just an algorithm that has 3 inputs. X is the first one, which is a string to be compressed. M is a target length, and epsilon is the error probability. And has one output, which is a string of length M. So, so the second input is the length of the output. So the output is a string denoted C epsilon M of X. And decompressor is the deterministic partial function. It's important that it is partial. This will make some parts of the theorem more difficult, but it's important. So a decompressor is a deterministic partial function mapping strings to strings. And we use the homograph complexity of X with respect to decompressor D as the length of the smallest p, so that D on input P is equal X. So we think that P is the description of X, with respect to the decompressor, we can see that the decompressor is also a descriptor or a description system. And KDX is the minimum description length with respect to D. Yes, it is the length of the smallest P, so that P describes X with respect to D. And we say that a compressor, we call it C-opt, is delta optimal. Delta is meant to be something small, it is called the overhead. So C-opt is delta optimal. If for every decompressor D, there is a decompressor D prime, so that for all X, epsilon, and for every target length M bigger than the smallest, the minimum length of X plus the overhead, the decompressor on the output of C-opt is able to reconstruct X with probability 1 minus epsilon. Yeah, so this is also, it has, we call it also a universal compressor because it works for every decompressor. There is just one compressor that compresses X. The university better. So this is the main result formally. There exists a C-opt with a small overhead. The overhead is just log M times log the length of X over epsilon, and which is computable in probabilistic polynomial time. Okay, so this is a main result. Okay, so again, it is restated here. So let me try to describe in words what it says. It says that this C-opt is one single fixed compressor which has this quite property that for any compressor pair, so for CD, and also say no matter how Zimand is uncomputable, any other compressor, she's almost the almost as good modulo this overhead as any compressor, but in addition is fast. So by fast I mean it was in probabilistic polynomial time. Okay, so there is a caveat that the decompression of the code was produced by this universal compressor actually may be slower than the decompressor corresponding to C. Okay, so we gain that we can compress fast and without losing too much in the compression length, just a small overhead, at the price of perhaps a slower decompression. Okay, so this is the main result, and just some particular cases. The first particular case is a fast compression to almost minimum description length. So here we fix U an optimal universal 2D machine. You should think that U is this decompressor, and then what I presented before as KDX. Now for this U, this is just a standard definition of Kolmogorov complexity. Yes, and by optimality, it means that KUX is at most KU prime X plus a constant for any U prime, and the constant only on U prime. Opt on input X as the Kolmogorov complexity of X and epsilon produces in polynomial time a code word X of length pre-Kolmogorov complexity. The overhead is just big of log n square. And epsilon is error probability. Okay, so what we said is that given x, k of x, one can compute a shortcut. If you know the x of the shortcut description by brute force, you can find this can be done not by exhaustive but it can be done in polynomial time. So far, I'm kind of still here.
I think we're losing. You're breaking.
Hello.
Something is wrong with the connection, at least from my end.
Yeah, my end too.
So did you were you able to follow me so far or not really?
Sort of.
The last slide
Great.
was the worst. Let's put
Maybe
our
you can-
videos down. Maybe
You can try to cut the video.
Yeah.
Not the presentation, but the camera. Invert.
Și de la tine, Gabi, că și noi transmitem lui și atunci merge greu.
So now do you see my screen?
Yes.
Okay, thank you. So I'm not sure how much you lost. Maybe I'll just stick to presenting the result and I will skip everything about the proof. So again, the bottom line is that when we compress, there are three objectives. We want the compressed word to be as short as possible. And we want fast compression and fast decompression. And what we have shown is that it is possible to achieve the first two simultaneously. While it was well known that number 1 and number 3 were impossible to achieve simultaneously. And in particular, it means that we can compute a description of a string which is very close to the cohomology complexity of it, if we know the length of the smallest description, or even if we know a bound on the length of the smallest description, we can produce a codor having that length plus a small overhead in very fast in probability polynomial time. And also another application is for the so-called document exchange problem. So here is this problem we can think as a game, let's say, between Alice and Bob. So Alice has file X and Bob has an old version of that file Y. And Alice would like to update Bob. And the question is, how many bits does Alice need to send to Bob? And of course, there is clearly she needs to send at least the cohomology complexity of X given Y. And our result implies that actually Alice can compute a string having that length plus a small overhead. Even more, she can do this in probability polynomial time, so that Bob can reconstruct from the old version Y and the string Z that Alice has sent him, the updated file. And what is remarkable is that Alice can do that without knowing what information Bob has. Okay, sorry for that. Okay, so because I don't have time, I will skip the proof. I'll just mention that the idea is to use something called the lossless expander. And what the lossless expander is, it's a bipartite graph, which has the properties that for, so it has the bipartition. Here we have the left nodes and we have the right nodes. And it is an expander, meaning that for any set S on the left of size at most k, the number of neighbors is 1 minus epsilon times d times the size of S. Okay, so the number of neighbors is S close to maximum. The maximum would be d times S, where d is the left degree. These graphs are left regular, so each node on the left has the same degree d. And by an extension of Hall's theorem, for every set S, there is a matching that assigns to each element in X 1 minus epsilon d of its neighbors. And then the idea is that we simply compress X by randomly picking one neighbor. So according to this matching, it is possible to reconstruct from a random neighbor CXX with property 1 minus epsilon just by doing the matching. And there is a problem because we actually don't have matching here. We have online matching because this set S in our case may be produced online. And then Hall's theorem does not work, but there is a way around this. So roughly speaking, this is at a high level the idea of the proof.
So what is so the expander gives us the encoding, the compression.
Sorry?
How does the expander connect with the compression? It's basically like
So with the compression.
Yeah. Mm-hmm.
So this set S is the set of programs of length at most k that the set of descriptors. One of them would be the descriptor of our X, and the decompressor has to find that one. Mm-hmm. So the decompressor can build this set S. So this is like the set of suspects, and then the compressor needs to provide a fingerprint that enables the decompressor to prune the set of suspects so that the decompressor is able to. So the idea is that if we just randomly pick a random neighbor of S with high probability because of the property of the lossless expander, this is matched with X. So from CX, indeed, as a set S, the decompressor can, by just running the matching algorithm, can find X. Yes. So the decompressor can build the set of suspects. And because the compressor provides a random neighbor of X, this can be matched by the matching algorithm with X, so the compressor can find X. That's the idea. Does not quite work because, as I said, the compressor only knows the set of suspects in an online manner. And Hall's theorem does not work for online matching. This is here is an example. So here we have a bipartite graph. If we take any two nodes on the left, for example, if we take this node and this node, we can match them like that. But if we take this node and this node, we can match them like that, yes? So this graph has offline matching, but it does not have online matching because, for example, if this node comes first, we must choose now to match it with this node, but now we are in trouble because if this node arrives next, there is no match for it. So online matching is quite different from offline matching. And well, we have some tricks to go around that, or maybe more than a trick. But again, unfortunately, I don't have time to go over this part. So I will skip, and I will maybe just say a few words about Slepian-Wolf coding, which is just a fancy name for distributed compression. So here we have an example. So Alice, she has a line L, and Bob has a point P. So Alice has L and Bob has P, and they want to send this L and P to Zach. And well, let's say that you work over the affine plane over the field with 2 n elements. So the line has 2 n bits elements because it is given by the slope and the intercept. And the point P also has 2 n bits, the 2 coordinates. But together, because of the geometric correlation, L and P have 3 n bits. Yes, if we know the line, P's can be given just by 1 coordinate, for example. Okay, and the question is, how many bits should Alice Bob send to Zach for Zach to reconstruct L and P? So clearly, they need to send at least 3 n bits, because L and P together have 3 n bits of information. And Alice alone must send at least n bits, because even if Bob has the point, the 2 n bits, he still needs n more bits from Alice. And similarly, Bob has to send at least n bits. And so these are the necessary conditions, yes? So if Ka is the number of bits sent by Alice and Kb is the number of bits sent by Bob, Ka plus Kb should be at least 3n. And Ka should be at least n, and Kb should be at least n. And what the Slepian-Wolf theorem says that these necessary conditions are essentially also sufficient. So any numbers satisfying these constraints are achievable. So for example, Alice can send 1.5 n bits and Bob can send 1.5 n bits. Or Alice can send, I don't know, 1.7. Yeah, so Ka, for example, can be 1.7 n and Kb can be 1.3 n bits. So any number satisfying these constraints are okay. This is a classical theorem from the 70s. But it has this caveat that it was under some assumptions, which essentially is saying that the data that is sent, this is just an example here, just with a line on the point. The theorem is much more general, but nevertheless, the data has to be generated by some stochastic processes that are simple. So the information that Alice and Bob sent to Zach is random, but random generated by some processes that are kind of simple. And using our optimal compression, we have shown that actually we don't need such an assumption. So yeah, I see my time is over, and I will just stop here. And sorry for the mess.
Mulțumim. Întrebări, dacă sunt. questions, sorry.
I'm sorry, I made an experiment with you, trying to use my tablet, and
So the compression is efficient, but somehow there is some existential type of result. I mean, it's an existential. No, it's not. Wait. No. Do we? I mean, the algorithm for compression is explicit, or we say, or you show that there exists an algorithm. I don't know. Is my question. Does it make sense?
okay, I think I can hear you now. So can you repeat?
Okay. So you can exhibit an algorithm, or you show that there exists. I mean, just existentially, there exists some efficient algorithm. I mean, just existentially. Is there something canonical?
No, I'm sorry, I lost again some connection.
So the question is whether you can show an explicit algorithm that is efficient for compression, or you show just existence of some algorithm.